Hey guys, and welcome to your first organic lesson. I think it's first that we define what organic is, what organic means. An old definition of organic chemistry is the chemistry of compounds from living organisms. So anything that is or has ever been alive, the compounds that compose that organism, that thing, are organic compounds. But a better definition that we use now, more because it's more broadly applicable, is compounds that contain carbon. There are a few exceptions to this, as in they're considered organic molecules, but they don't actually have carbon in them, but compounds that contain carbon are organic compounds. In this class, we will focus on the top right corner of the periodic table almost exclusively. We'll see a few metals mixed in here and there. So carbon is really important because it's the foundation, or it's an atom found in many of the molecules that we interact with day to day, as in proteins, lipids, nucleic acids, all of our food, our clothing, all kinds of things. Carbon is found in all of them. So organic chemistry is all about carbon, but what the heck makes carbon so special? Why are there two classes at this level dedicated to carbon and molecules that contain carbon? There are more classes than that at higher levels, but two courses in organic chemistry sequence. Is it really that interesting? Well, if you look at the second row of the periodic table, I hope you remember that fluorine over here on the right, probably a little nugget of something that you remember about fluorine from general chemistry is fluorine is a very electronegative element. That means he loves electrons. Fluorine loves electrons. Conversely, lithium over here, he's on the other end of the spectrum. He hates electrons. He is not very electronegative. So along this hater-lover scale, we have carbon sitting neutral right there in the middle. Carbon is good at accepting electrons if the situation requires it, or giving electrons if the situation requires it. Carbon is a neutral compound. He goes with the flow. So carbon is very good at sharing electrons. In all of these carbon-containing molecules, we're going to talk about bonds that they make. Because in this class, we're concerned with the top right quadrant of the periodic table, that's where all the nonmetals reside. So nonmetals, remember, make covalent bonds. When nonmetals get together, you can make bonds to a lot of different atoms, as in carbon can make bonds to a lot of different atoms. Oxygen, nitrogen, fluorine, chlorine, bromine, iodine, hydrogen. Those are some of the most common bonds that carbon makes, but he can make more than that as well. So we said nonmetals make covalent bonds, but what happens when you have a metal and a nonmetal? Those make ionic bonds. When you have an electropositive element, aka a metal, and an electronegative element, aka a nonmetal, something from the left half of the periodic table, the left lots of the periodic table, and the right little bit of the periodic table, when those two things get together, you make an ionic compound. One of our favorite examples of an ionic compound is sodium chloride, regular table salt. Sodium is the metal, chloride is the nonmetal. Sodium normally has 1 electron and chlorine normally has 7. But because sodium is a hater, he gave electrons to chlorine, making him chloride. So sodium lost an electron, chlorine gained an electron. We got charges to show who gained and who lost. They fully exchange electrons because it's a metal and a nonmetal. You've got a hater and a lover in a mixture together. Why does all of that matter to us if we're only concerned about the top right quadrant? Well, we will come across a lot of ionic compounds throughout this class. The focus of the class is the covalent stuff, but we'll come across a lot of ionic things. One thing that I need you to know about ionic things that is that in water, ionic compounds dissociate. That means they separate into individual ions and they become solvated or hydrated if that solvent is water. So this is my little cation here. And the O from water is pointed toward my cation because remember dipole stuff. We're going to refresh your memory momentarily. but dipole sus says the oxygen has to point toward the positive charge. Here's my anion of my ionic thing and hydrogen from my water. All the hydrogens are pointed toward my anion. We're going to go through dipoles again. Hold on. But the process of solvation is what this picture is showing you. Remember, there are solubility rules, and not all ionic things are soluble, but the good news is most of the ionic things we interact with in this class are water soluble, because most of the time we will see a halide salt in this class, or a group 1 salt, as in something hooked up with lithium, sodium, potassium kind of thing, or something hooked up with fluoride, chloride, bromide, iodide. You'll get the drift as we move along. So we said covalent is really where we focus because we're talking about the non-metals in here. We're talking about carbon as our main focus. There are 2 types of covalent bonds. There's a nonpolar covalent bond and a polar covalent bond. What's the difference? Why do we care? If you have 2 atoms connected together that are equally electronegative, they share electrons equally. So the bond between those things, as in this hydrogen-hydrogen bond, those electrons are equally shared between those hydrogens. However, if you have 2 atoms that are different electronegativity, like H and F, you have a polar covalent bond. So electrons are not equally shared between these 2. We have electrons being pulled more closely toward the fluorine because fluorine is more electronegative than hydrogen. So this thing that I drew, I hope you remember, is called a dipole. We will talk about dipoles quite a bit. How do I know if a bond has a dipole or not? Here's a table of electronegativity values for most of the elements we will interact with in this class. And the arrows here show you the trend in electronegativities. It goes toward fluorine. Fluorine is the most electronegative element on the periodic table, period. So you need to know these trends. You do not need to know these values. We're going to use the trend to say, is there a dipole along that bond? Yep. So one thing that I do want to point out, hydrogen over here does not fit the trend. It's an outlier in that it really kind of squeezes right between boron and carbon in value of electronegativity. So hydrogen doesn't exactly fit the trend. I need you to know he fits between boron and carbon. Hydrogen is less electronegative than carbon, but more electronegative than boron. Okay, so ionic compounds, we said, most of the ionic compounds we interact with in here will be soluble compounds. Not so much for covalent compounds. Covalent compounds do not dissociate, and not dissociating means they are generally not soluble in water. Yep, okay, cool. So here are some colorful pictures that show you electron distribution within molecules. As we said just a second ago, in a hydrogen, H2, hydrogen gas, in a hydrogen atom, in a hydrogen molecule, these are the same electronegativity, so those 2 electrons in the middle are equally shared between the 2 hydrogens. That's this electrostatic potential map shows a completely greenish, yellowish distribution of electrons. It's all one color because all the electrons are evenly spread. Is that true over here? Nope. This blue says there's not many electrons on this side. This red says there are a whole bunch of electrons on that side. So as we just saw, when you have hydrogen connected to fluorine, there's a dipole pointed toward fluorine. That's where it gets red on the fluorine side and blue on the hydrogen side. So remember, in dipoles like this, the arrowhead is pointed toward the more electronegative atom always. So that dipole along that bond causes that fluorine to have a partial negative charge. It's not a full negative, it's a partial negative charge. And if you aren't sure what my symbol is right there, it's a lowercase delta. It's a partial negative. On the other hand, because fluorine's pulling the electrons, it means hydrogen is losing some electron density. So hydrogen has a partial positive charge. That's also a lowercase delta. Anytime you have a dipole, this back end will be the partial positive end. This arrowhead end is the partial negative end. In lithium hydride, LiH, hydrogen is more electronegative than lithium, so the dipole points toward hydrogen, and the colors tell me that. Okay, so how do you get from bond dipoles to, is this molecule polar or not? Well, we have to know bond dipoles, first of all, and remember electronegativity differences between atoms are what create bond dipoles. Here are some common bond types that we will come across in this class, and there are actual mathematical numbers to tell you how big the dipole is, because not all dipoles are created equally. Well, let's point out a couple of things. If I look at HF and HO, we know that fluorine is the most electronegative element on the planet, and oxygen is a close second. So it makes sense that the HF bond has a bigger dipole number here than the OH bond, because fluorine is more electronegative. Fluorine is more electronegative, it's pulling harder, making a more severe dipole. Okay, cool. All of this translates into, we're going to see some really large molecules in here, and it all breaks down. It all goes backwards to say, are there dipoles? Is there a dipole along this bond? Is there a dipole along that bond? Is there a dipole along every bond in the molecule? And then you have to add up all those dipoles. If you determine, yes, there is a net dipole in the molecule, we would call that molecule polar. Remember, net dipole is going to be after you've added all of the dipoles along all of the bonds together. And in order to do that and figure out if you have a net dipole, you're going to need to know about the geometry around the atom. Yep. Tetrahedral, trigonal planar, linear, trigonal pyramidal. Yep. It's all coming back. Okay, cool. So since we are all about carbon and molecules and bonding, it makes sense to start with drawing Lewis structures. So as I have already assigned, you should start working on the names of the alkanes in table 3.1 of your textbook. That table 3.1 says the name of CH4 is methane. So instead of just memorizing them, let's explain why the names are the way they are. All of these have a prefix. That prefix, this one is meth. Meth means one carbon. Ane is the suffix. Ane means this molecule belongs to the functional group family of alkanes. What is an alkane? It's something that has carbon and hydrogen only and all single bonds. So methane is an alkane. So knowing that, breaking down that name, I can know that this is my Lewis structure of methane. What? Yeah. It's got to have carbon and hydrogen, all single bonds, so none of these bonds should be double. Carbon is in group 4 on the periodic table. What that means is he has 4 valence electrons. Hydrogen is in group 1 on the periodic table, so it has 1 valence electron. But there are 4 of them, so that gives me a total of 8 electrons to draw this Lewis structure with. Well, carbon being in group 4, it actually tells me it needs 4 more electrons to give it an octet. And needing 4 more electrons means making 4 bonds. Carbon loves to make 4 bonds. Carbon needs to make 4 bonds. Hydrogen, it's not trying to get to an octet. Everybody wants an octet, but not hydrogen. Hydrogen wants 2 electrons and only 2 electrons to fill its outer shell. So hydrogen needs to gain 1 electron in order to fill its outer shell. So it needs to make 1 bond. So it's a perfect merriment. Carbon wants to make 4 bonds. Hydrogen wants to make 1 bond. So hook them up like we did. Ta-da! That's methane. This Lewis structure, though, seems to indicate that methane has a bond angle of 90 degrees. But that is not true in how methane really bonds. Methane really bonds, like this picture down below, this one, to give you a 109.5 bond angle. Yep, it does. So in order to achieve a 109.5 bond angle, you're going to have 2 of your hydrogens in the same plane as carbon, Plane plane, in the same plane as carbon, and 2 of the hydrogens are out of the plane. This one with a dash is going in to the paper. It's going away from you. This one that's got the heavy wedge, this guy, this is coming out at you. It's coming toward you. So that is a 3-dimensional representation of my methane molecule. It is perfectly acceptable to draw it this way. We will draw them like this all the time, especially in the beginning. But we also need to recognize that this is what methane really looks like. It's a 3-dimensional representation with 109.5 degree bond angles. Okay, cool. Something that has 109.5 degree bond angles is called tetrahedral. So something with 109.5 degree bond angles is tetrahedral. I'm going to erase this 90 degrees so that you don't get confused in case you nod it off. So a tetrahedral molecule, 109.5. I hope you also remember from Gen Chem that something tetrahedral 109.5 we say is sp3 hybridized. Something that has 4 different directions where it's making bonds. Those 4 different directions tell me I've got 4 domains of electrons around this central atom, and 4 domains tells me that thing is sp3 hybridized. So this carbon is tetrahedral, it's sp3 hybridized, it has a bond angle of 109.5. Okay. Do these bonds in this molecule have dipoles? Yep. Every single bond has a dipole pointed toward the carbon and away from the hydrogen because hydrogen is less electronegative than carbon. So if I take those 4 bond dipoles, considering that this molecule is tetrahedral, do I come up with a net dipole for this thing? Nope. And because I do not come up with a net dipole for this thing, I'm going to call this molecule nonpolar. I can look at my little green graph down here and see that it's green, greenish yellow. So the electrons are evenly distributed throughout that entire molecule. Nobody has extra, nobody has too few. They're evenly distributed. That greenish-ness also tells me that compound is a nonpolar compound. Whew, that was a lot. Let's do another one. What about a 2-carbon alkane? Remember, alkane means all single bonds. So 2 carbons, put hydrogens everywhere around it in order to make carbon have how many bonds? 4. Carbon makes 4 bonds. So this molecule is C2H6. His name is ethane. That ane, remember, means alkane. F is the prefix for 2 carbons. Meth means 1, eth means 2. Hopefully you already know. Prop means 3, bute means 4, pent means 5, etc., etc. Yeah? So here's a 2-carbon alkane. His name is ethane. This ethane looks to have 90-degree bond angles in this Lewis structure I drew, but that's not legit. It really has 109.5-degree bond angles as well, because there really are 4 domains of electrons around this carbon and that carbon. So this 3-dimensional representation down here, remember, this guy is coming out toward you, that one is going away. This one's coming out toward you, that one's going away. We will talk in great detail about all of these, and we will draw tons of them, but not until next week, actually. We're going to let you get your bearings first on drawing Lewis structures in general this week. But stereochemistry, this stuff, next week. Okay, so I noticed that this molecule is green. Green electrons are fully distributed. If there are dipoles along these bonds, and there are dipoles along those hydrogen-carbon bonds, not the carbon-carbon, but hydrogen-carbons, if there are dipoles along those bonds and I sum up all those dipoles, considering that those carbons are tetrahedral, do I get a net dipole? Nope. So with no net dipole, that means this is a nonpolar molecule. So this nonpolar molecule has electrons evenly distributed all throughout the whole thing. Okay, cool. That's methane and ethane that we've drawn. I bet you could draw propane as well. This is propane. You link all of your carbons together and fill up hydrogens so that each carbon is making 4 bonds. Methane, ethane, propane are all part of what functional group family? Alkanes. So we are all about functional groups in this class. We are all about functional groups. Your first mission is to memorize some functional groups, because I hate memorizing, but there's a little bit of groundwork you got to do. Memorizing functional groups, because we need to recognize when we come across a similar functional group that it will do similar things and yield similar results. The first place where we'll see functional group things is in this kind of thing. This is called an IR spectrum, an infrared spectrum. IR is what we will call it all the time, infrared, IR. This IR spectrum was taken of ethane. There are a couple of things that we need to know about the IR spectrums in general. An IR spectrum can be broken into 2 regions, 2 sections. This section on the right, from about 1500 inverse centimeters, that's wave numbers, it's a frequency number, from about 1500 until the end of the spectrum, which is often 500, even though it's not listed on there, that's called the fingerprint region. We really don't care very much whatsoever what shows up in the fingerprint region. We're not gonna, there are 2 peaks right there. We don't care. We're gonna pretend they're not there because they're in the fingerprint region. Over to the left, that's called the functional group region. We do care about what's in the functional group region. And I see that there's a giant set of peaks here. That giant set of peaks should be labeled as an sp3ch stretch. What the heck? We're not going to go into the IR theory about why this happens the way it does, really, in depth, but different bonds stretch at different frequencies. When I put ethane in an IR instrument and I hit it with some energy, that ethane responds in unique ways, and the bonds in that ethane respond in unique ways also. Those bonds stretch. And so this chunk of peaks that I see right here is indicative of this type of bond stretching, a carbon-hydrogen bond stretching. It's not just any carbon-hydrogen bond, it's very specifically an sp3 carbon-hydrogen bond. So ethane has only sp3 carbons, so that's why we can group all of this chunk of peaks together. That grouping of peaks are sp3ch stretches. Whew, that was crazy. Why does this matter? Why are we talking about this on the first day? Well, I told you, functional groups are the foundation of everything we do. And ethane is part of what functional group? Alkanes. Here's an IR spectrum. We're going to say 1500 and everything to the right we don't care about. All I see is this big chunk around 3000. It's officially just to the right of 3000, which is an important distinction to make. But peaks, chunks of peaks just to the right of 3000, those are sp3ch stretches. So since that's the only peak that I see in this IR spectrum, regardless of this fingerprint region, remember, that's the only peak I see, this is a spectrum of an alkane. Because I picked it out, obviously, I know that it's the spectrum of this 6-carbon alkane. What's the name of this 6-carbon alkane? Hopefully you're shouting in your bedrooms, on your couches, at your kitchen tables. It's hexane. So this is the IR spectrum of hexane. Remember, what did we call the whole left bit of this IR region? The functional group region. As you can imagine, all alkanes have very similar spectra. Whether it's methane, ethane, propane, butane, pentane, hexane, heptane, etc., they all have very similar spectra. It's all about the functional groups. Okay, well, let's learn a new functional group. Are you ready? C2H4. The 2 carbons are definitely connected. And so I'm going to spread out the hydrogens so that it's kind of symmetric looking, because that seems most appealing to me. But carbon needs to make 4 bonds, and these carbons are only making 3. So if I double up and make a carbon-carbon double bond, double bonds, remember, are 1 sigma bond, that's a lowercase sigma, and 1 pi bond. That sigma and pi is important in drawing these kinds of molecules. A carbon-carbon double bond belongs to the functional group family of an alkene. Yep, it's real similar to alkane, but it's an alkene. Alkenes and alkanes, very similar. If you speak it in the right southern drawl, they sound the same. Alkanes and alkenes. Alkanes, single bonds. Alkenes, carbon-carbon double bonds. Okay, cool. C2H4, let's name that guy. C2, well, that's obviously S, but it's not an ane anymore. It's an ene to tell you it's an alkene. This molecule has an alkene in it. So since these carbons don't have 4 domains around them, they've only got 3 domains of electrons, aka 3 directions that electrons are pointing. This direction, that direction, that direction. 3 domains of electrons around it. 3 domains of electrons tells me that this is an sp2 hybridized carbon. sp2 hybridized carbons have 120-degree bond angles, and things that have 120-degree bond angles are trigonal, planar. That says this molecule is flat. So if I look at my 3-dimensional molecule down here, there are no dashes, no wedges, no difference in how those bonds are drawn. That's because this molecule is flat, and all 6, 1, 2, 3, 4, 5, 6, all 6 of those atoms are in the same plane. It's a flat molecule. Notice there's a bunch of green on the outside of this, but red on the middle. Well, that tells me that there is some unequal electron distribution. But is it a polar molecule? No. So prior to now, we've sort of been pointing to this molecule down here and saying, if it's all green, it's nonpolar. We're still going to say this is a nonpolar molecule because the dipoles along these bonds would perfectly cancel out because they are all equal and opposite. They're all pointed toward the carbon, away from the hydrogen. They cancel each other out. So this is still called a nonpolar molecule because it has no net dipole. But I do want to point out something. This little red electron density here, why is it red? Red means you have extra electron density. Remember I said a double bond is a sigma and a pi bond. That pi bond is responsible for that extra redness, that extra electron density. When we start doing reactions, alkanes and alkenes do not do the same types of reactions because they have unequal electron distribution. The alkane was totally green, greenish yellow, and all alkanes would be green, greenish yellow. All alkenes are going to have this little pudgy red bit in the middle, and alkenes react differently because of that pudgy red bit. Yeah? Okay. Let's take a look at an IR of an alkene. This is ethene. Yes, I know it's called ethylene. We'll talk about naming one day. This is the IR of ethene, and at first glance, it might look pretty similar to the last one. But our fingerprint region, remember, ends about 1500-ish. So there are peaks. There are two sets of peaks outside of that fingerprint region. Two sets of peaks in the functional group region. I know it's kind of hard to tell, but this set of peaks on the left area of my functional group region, this set of peaks is not in quite the same area that it was in my alkane spectrum. So there's my ethane spectrum. See, these, they're not perfectly aligned at the bottom, I know, but these peaks are more to the right, while those peaks are more to the left. Does that matter? Because it's really telling me that the bonds in this molecule are different. They stretch differently than the past ones. This is not an sp3CH stretch, it's an sp2CH stretch. Still a stretch, still a CH bond that's stretching, but a different hybridization of your CH. Most alkene IR spectra will have this sp2CH stretch area. It actually has to have a C bonded to an H as part of your alkene in order for this peak to show up. So what the heck is this other peak over here that's in our functional group region? That's the C double bond C stretch, a carbon-carbon double bond. An alkane does not have that, but an alkene does. You guessed it, all alkenes have very similar IRs because it's all about telling you functional groups. Okay, let's get one more under our belt. How do you draw C2H2? C2H2, that's going to be carbon connected to carbon. And let's distribute our hydrogens equally. Carbon needs to make 4 bonds. This is not good enough. So let's put a double. Still not good enough. Put a triple. That's better. This is C2H2. It has a triple bond. Triple bonds, I hope you remember, are 1 sigma, lowercase sigma right there, and 2 pi bonds. Yep. It's a C2, so it's still an F, but it's an F-ine because a carbon-carbon triple bond is called an alkyne. So this carbon does not have 4 domains of electrons around it. It does not have 3 domains of electrons. It has 2 domains of electrons. And something that has 2 domains of electrons is called sp hybridized. It's a linear molecule, which means it has a bond angle of 180 degrees. The hydrogen carbon-carbon bond angle is 180 degrees. It's a linear molecule. There's my drawing down below. Note there are no dashes, no wedges, because it's linear. This electrostatic potential map over here is pretty interesting. There's some red little squishy stuff in the middle. That's because the alkyne has two pi bonds, and those two pi bonds are responsible for the red middle. What that means is the pi bond in an alkyne and the pi bond in an alkene have similar characteristics, so they do similar things. They have similar reactions. But there are differences as well. There was no blue region on my alkene previously, but there is blue on this alkyne. This alkyne has some characteristics different from alkenes. Some similar because of the red, some different because of the blue. Do you suspect alkynes and alkanes react similarly? No way. Ready to see an IR? Here's an IR of an alkyne. Yes, the name is acetylene. It's really ethyne. We'll talk about the naming one day. We don't care about all this stuff over on the right. This is my functional group. This is my fingerprint region. Who cares? So I see two major things that I need to label in the functional group region. I see that peak. You see where that's at? It's way further to the left than even an alkene was. I hope you can guess that's an SPCH stretch. In addition to an SPCH stretch, an alkyne should have a C triple bond C stretch, just like the alkene had a C double bond C stretch. This one is inverted and pointed north. That's not typical. It's usually pointed south like that, but we won't obsess about it. Today is the first day. We're introducing you to what the heck IR is, what functional groups you need to start learning, and how to draw Lewis structures. I think that's good enough for today.